So yesterday we studied the linear constant coefficients transport equation, and let me recall you the equation. This is homogeneous, the solution is explicit, provided that you give u0 z provided that you give this okay, or if you want, maybe yesterday I wrote 0z b sigma. This was the setting of yesterday. The point is that the solution is explicit. We wrote yesterday if you zero using C1, sigma is identified with a rank. Okay. Then the solution, the unique solution, we know it is given by this. Okay. Now this is clearly C1, but even if this equation is extremely simple, one can ask the following question. Suppose now that U is not necessarily C1, so what if you, example, problem, if U0 is not smooth, and we pretend that this maybe still has a sense with U0, say for instance discontinuous, then in which sense this PDE is solved? Because if this is not C1, then we cannot write this pointwise. Yesterday the solution was intended pointwise, point by point. At each point I computed the derivatives, this must be 0. In which sense we have to interpret the PDE. So, and the idea, okay, one possibility would be, so, problem, example, okay. Suppose that n is equal to 1, and suppose that u0 is equal to the characteristic function or of, say, by characteristic for me now, okay, because a characteristic could have values 0 and 1. Okay, yes, 0 and 1, it's okay. 1 if x, if z if z is positive, 0 if z is negative. Now, this is discontinuous, clearly. And the point is that why don't we define u of tx still equal to u0, provided, of course, this is not defined at this point, doesn't matter, almost every defined. This is not defined where x is equal to ta, doesn't matter, almost everywhere defined in R2. Because it is not defined on the line x minus ta equals 0. This doesn't matter, it's defined everywhere. Say 0 here, 1 here. So it's defined everywhere, and it satisfies the PDE almost everywhere. Because clearly it's piecewise constant, it's constant here, constant here. I fix a point out of this line, ut is 0, grad u is 0. So this is a solution almost everywhere defined. So one first attempt could be to interpret this, maybe require validity only at almost every tx, with respect to the Lebesgue measure, say, okay. Now consider instead the following function here. Another function, v of tx equal independent of it is clear that this solution takes the initial condition. At time 0 it is equal to u0. But it is also clear that I can consider this function now, which again takes the initial condition, clearly. It does not depend on time, so the solution does not move, fixed, no evolution. And still, it is a function which jumps here, no, 0 here, 1 here, jumps on this line, and again is an almost everywhere solution. In this way, you can construct so many almost everywhere solutions, as many as you want, keeping the boundary, keeping the initial condition. Okay? So this is saying that somehow it is not a good idea to consider the solution in the almost everywhere sense, because at least you lose for sure uniqueness in this way. So you relax too much, you relax, the notion of solution in a way that you have too many solutions. Okay? So let me give you now, so almost every maybe is not a good idea, so let me give you now a definition. What could be another possibility? Could be this one. Suppose that you don't know that U is smooth. Okay. But you have your PD. We know one of the various formulations of yesterday was this one, clearly, no? Now, suppose that you multiply, this is formal because your solution does not exist, is not smooth enough. Now, formally you have this, formally you can multiply by a very smooth function, phi, with compact support, say. You multiply formally by this. Then you integrate in space-time. Huh? And now you integrate by parts. So you integrate by parts. This means that this is integral in time and space-time. So this integral in time, you can do this by part, formally. Minus tu. Maybe then, this is very formal, then I will give you the definition, precise definition, but just only to convince you that we can give another definition. Phi say is C1 with compact support in some region omega of time space. Suppose that, say, omega for simplicity, say, is well, if it has compact support, then this is integral 0t, this is integral Rn, 0t, Rn. So this now I can integrate by parts. And then I can use the divergence theorem here. What is, let me recall you a general form of the divergence theorem. Say, theorem. Maybe. So let omega in Rn be open, bounded, with Lipschitz boundary. Lipschitz boundary should be defined. It means that locally the boundary of omega can be written as a graph of a Lipschitz function with respect to a suitable orthogonal coordinate systems, and omega lies from one side of this boundary. Okay? Lipschitz means that I allow, for instance, omega having coordinates. Omega could be this. Omega could be this. It's important to not to have omega smooth, because omega smooth is too restrictive for the applications. So we can have omega not really smooth, but almost, say, in the sense that the boundary is locally graph of the Lipschitz function. Omega is here, and moreover, it is possible to show that under this assumption, the boundary of omega has an almost everywhere defined unit normal. This is famous theorem by Rademacher on differentiability of Lipschitz function almost everywhere. So, in particular, there exists, say, the outward unit normal, outward unit normal vector nu, that we call it nu omega at y, for almost every y on the boundary of omega, where now this almost is surface measure. You see, this solid cylinder is omega, the boundary is just the floor, the top, and the lateral boundary. Of course, in these points there is no unit normal to the surface. Here there is, here there is, here there is, there is, but along this circle there is no natural definition. There is not a unique unit normal here, pointing outside, because the manifold is not smooth, right? But these are curves, one-dimensional, in a surface which is b-dimensional, two-dimensional, and so they have zero two-dimensional measure. Okay? And the same for the square, where there is no unit normal, the vertices, but the vertices are points which are not seen by the one-dimensional measure. Okay? So let me denote this is a famous measure. I don't want to insist for the moment. This is called n-1 dimensional Hausdorff measure. It's the dimension of the manifold. The boundary of omega is n-1 dimension. Okay, so let omega be open bounded, which is Lipschitz boundary. So there is almost everywhere with respect to this measure a unit normal pointing outside. In the violet curve, the unit normal is not defined, doesn't matter, it has zero measure. Okay. Lipschitz boundary, and then let say eta from omega into Rm, a vector field with the following. Suppose that eta say is let me write down the statement, then the integral over omega of the divergence of, we need some smoothness here. So let me take eta, say C1, simplicity, intersection, I don't have to write, sorry, on the right of this line. Then let then the following divergence theorem holds. Gauss-Green or divergence theorem. Divergence of eta dx equals plus scalar product of eta against the outward. If you put the plus, you need the outward. Plus 1. If you find in the books, you find the minus, it means that they are using the invert, changing normal, sign of the normal. Ni omega. 1. Okay. This is one of the most important theorems in analysis. This is one possible way. It is not the most general way one can write it, but for us, I think it will be sufficient. Okay. And I hope it will be sufficient. Okay. Now, why I'm saying this? Because now here the fact that the most inner integral was time, in such a way that I can integrate by parts first in time. Here the inner integral instead in space, so that I can use the divergence theorem. Why? I am integrating in Rn. It's true that Rn is not bounded, right? But I have here phi. Phi is compact support. Huh? Compact support. So actually, compact support. So phi is 0 out of a compact set. This means compact support. Support. So this means that this integral is actually not over Rn, but just only in some big ball containing the support of phi. So I am in the condition to apply this theorem formally. So that formally, because still I don't know that the regularity of u, but in any case, if I could apply the theorem, I would end up with simply the integral. Now I have this theorem, This theorem immediately implies the following integration by parts formula. So applying this to, instead of eta, you modified it and you multiply by a scalar. So what do you get? You get integral over omega divergence of phi eta. Huh? Instead of eta, I take multiply by a scalar function sufficiently smooth. So what is this? This is integral over omega phi divergence of eta plus integral over omega eta dot gradient of phi. Okay, this is just computing the divergence of the product. And this must be equal to this with phi eta in place of eta. Okay? This is called the integration by parts formula. This is the boundary term. So what does it mean? It means that phi divergence of something is equal to the boundary term minus this. Okay? There is actually this is simply minus grad phi dot I u. Do you agree with this formula or not? Or there is something, or I made some mistake. I want you to convince that this formula, because now this will be my definition. Oh, and now I will give you a definition after this. This is formal. Everything is formal. If everything would be smooth, this is okay. But is it really okay, or just I missed some term in the integration by parts? Did I miss something or not? So, for instance, when I do the first year calculus phi u prime equal minus u prime phi, but then there is a boundary term, the boundary of the integral. Where is this boundary term? It is not written here. Why?
Because phi is with compact support.
Phi is compact support. Okay. Compact support means that phi is 0 at 0 and at t, capital T. So there is no boundary term in this integration by part. And there is no boundary term here because, again, I am integrating over a big ball containing the support, and phi is 0 on the boundary of the big ball, so here this term is 0. No? Minus and minus. So, one possible. Now, this is 0 for any phi with compact support. Right? So, but now, if I adopt this as a definition, it's not bad. Which is the regularity of u sufficient to give a meaning to this integral and to this integral, in your opinion? Just the regularity of u. In order this integral to be converging, and this integral to be converging. Grad phi is continuous with compact support. This is a vector constant. So, in order continuous function with compact support, what is it is enough? It is enough to require that u is in L1 log. L1 log means absolutely integrable on compact sets. But this integral is an integral on a compact set on the support of this. So as soon as the integral of modulus of u is finite on that compact set, this integral is converging. And the same here. So definition. Let u0 just be in L1 log of 0 t times r n. We say that say that the function u in L1 log, sorry, u0 is the initial condition, is just in sigma. Sorry. We say that u in L1 log 0 t times Rn is a solution to, it's a little bit trivial because here I don't put the boundary condition, but just to start, is a solution to ut plus a grad u equals 0 in 0 t times Rn. Now I leave some space because the definition will be, I want to keep into account the initial condition. If for any phi compactly supported in 0t times Rn, integral 0t Rn u phi t dx dt plus integral 0t integral Rn a dot phi u dx. This is reasonable now. It's a solution in the sense of distributions, in the distributional sense. This is another possible way to give some notion of solutions. What is missing here is missing the boundary condition. So if I now, do you agree that this is just rewriting this idea? No? And u is not necessarily smooth, and L1 log is sufficient. But now what it is missing here, the boundary condition. I've given u0 in L1 log, so I have to impose that u equal to u0 in L1 log. So now I come back here. Which was the problem? The problem is that I am taking this is called test function. Phi is called the test function. But if I take phi, which is compactly support here, I will never see the initial condition on sigma. No? Because if I use this idea, when I integrate by parts, I don't see the value at 0. So, why don't we modify, which, in your opinion, now it is clear that I don't have phi u at t minus, no? Let me write down the f prime g equal minus fg prime plus fg b minus fga. I am using this, but if one of the two is 0 in A and in B, I don't see anything. No? So I can put this 0t for your convenience. Now, what happens in T is not relevant for us, but what happens in 0 is relevant, because that is the initial condition. So we have to improve a little bit this equation, this definition. So what is distribution solution to this and u equal u0 on sigma? If now we have to modify a little bit, what could be the idea in your opinion? These test functions are not enough. We have to enlarge the class of test function. For every test function, in which class? C1 is okay because C1 we differentiate once, phi t and graph phi. So C1, okay. But the point is the support. The problem is the support. So what we have to change the support. One possibility is the following. So instead of taking this support, which is too restrictive, we enlarge a little bit the class of test functions, and we define, say, C1, say I don't know how to call it. What is this? Say is a C1 function equal the function psi in C1 such that support of psi is compact in 0 t times r. Now, suppose that I change this definition and I take this test class of test function here. So my notation is C1. Let me check that I'm using the correct notation. Yes. Support, compact support, C1 tilde. C1 tilde at 1%. So this means that the support of phi is compact contained in 0 to okay, and phi is C1. This is what I mean by this symbol. Now I have enlarged a little bit the class of tests in such a way that now it's not true anymore. When I do this computation, I integrate by parts in time. This is not true anymore. There is another term. There is what? Integral over Rn phi of t u of t phi of tx u of tx minus integral over Rn phi of 0x u of 0x. This. But this is open. So a compact and this open, it means that I think that the capital T phi is 0. Right? So this is not present here. And what remains? Phi instead can be non-zero at time 0. Is it clear? We can finally motivate the definition, correct definition. Let U0 in L1 log of sigma. We say that U in L1 log is a distribution, it is a solution in the sense of distribution to this PDE coupled with this boundary condition if for any test function in this new class, now you see we have minus, minus, and minus. 3 terms with the same sign. I multiply by -1. Are you convinced or not?
For the last part, if we try to approach zero by the left, by continuity of phi, we should have also that.
Indeed, continuity phi, we have phi of 0 at x. Perfect, phi is continuous, C1. So I just restrict phi on the hyperplane. On the other hand, at time 0, u must be u0. So this is a way to impose u equal u0 at time 0. Because here I put u0. Right? So finally, this is a complete definition of the solution, weak solution in the sense of distribution, taking into account the PDE and the initial condition. But in the class of tests, the previous one that I wrote are not enough. I have to enlarge a little bit in order to test also what happens on sigma. Because if the test function is 0 on sigma, I will never see the boundary condition. But if the test function is also could be non-zero, then I see also, I can detect also the boundary condition. So this is, do you agree with this? So this is another way, one possible definition of solution. Now the point is, there exist solutions in this sense. What can we say? Is it unique? Because in the previous sense, the almost everywhere sense, which was apparently very natural, we immediately realize that we lose uniqueness. We have existence, but the class now, the solutions are not unique. Now, this is another notion of solution, but you are not convinced, I think. It seems to me not.
It's okay.
It's okay? Everything is clear?
But the T, I mean the big T, I mean, we are considering it finite, or I mean, it's like a finite time solution, or?
T can be, you're right, T has been fixed. T I think could be in 0 plus infinity. Principle B. Okay. So now let us do some. Now we have a new definition at our disposal. By the way, the idea of integrating by parts and put all derivatives as most derivative as you can on the tests, and leaving u without derivative or with less derivative is a crucial idea in distribution theory. I don't know, probably you have never seen what is a distribution, it doesn't matter, but the idea is to rewrite things and to put, using this integration by parts formula, and to put all derivatives instead of u, which we don't know, because u in principle is not smooth, put it on the test. Test u fi is smooth, we can do it. So many PDEs, at least the PDEs which have this structure in divergence form, say, because at the end we are using the divergence theorem, so we are using some divergence form of the PDE itself. Many PDEs of this form can be, to these many PDEs we can assign a notion of weak solution if necessary in distributional sense. Okay? So now let's continue with our. So we have an example that we discussed at the beginning, this characteristic function of, or more in general, a function taking only two values. U0 takes only two values, say. Okay, so example, say n equal 1, let u minus and u plus be two different real numbers. Okay. And take u0 of z equals, say, u minus if z is negative and u plus if z is positive. Then define u of tx equal u0 of x minus ta for all tx in R2, but with the constant then u is a distributional solution to So, what is the shape of this object? Let's try to do a picture. So, we have an initial condition u0, which is a step function. Then we have our characteristic lines. And then we can try to, I can try to draw sort of, can you see it? No. And also for negative times. So there is a vertical wall here. Is a distributional solution to this. So let me now come back to the, no, cannot use this page. So let me come back to this. So this is t, this is x. So we have this characteristic line. So this is the horizontal plane. Here corresponds to this. Here we have u equal to minus, u equal to plus. This is line x equal to okay. So now we have to do, now there is something to do. So this is equal to u minus if if x minus ta is less than 0, and u plus if x minus ta is larger than 0. Okay? Fine. So now we have some computation to do. So let me introduce one more notation. The jump of u, u is discontinuous, as you can see, it takes only two values. The jump of u is a subset of R2 and this line here, jump set. Okay, let me indicate, then the color seems almost the same. So I change color. I take this one. Jump of u is the set of tx where u jumps. So this is just this line. Is this x minus ta equals 0 in the tx plane. Okay. Okay, so now I have to take a test function, and what do we do? So I have to show that this is a distribution solution. There is something to do. So let me go on with the computations. Okay, so let me introduce jump of u, as I said. So let me call omega for simplicity, maybe. Yes. Omega equal, say, 0 plus infinity. Let me see. Omega 0 plus infinity times r. Okay, so let me now, for the moment, just look for positive times. Okay. Jump of u is the set of all tx in omega such that x equal ta. Okay, so now let me remove the negative times for simplicity. So, okay, let me give you some other notation. So, okay. So omega minus, let me call the set of tx in omega such that, so and omega plus and then this is the jump. Huh? Now take a function phi in the class C2 R2, support of phi compact, contained in 0 plus infinity times r. So take a test of the form discussed before. Okay, so what we have to do, we have to start to compute integral. So we have the integral over omega. Let's start to compute. Oh, as a notation, since we are in one space dimension, I just, for simplicity, write this. Okay? Since n is equal to 1. So we have to start to compute this. Okay? Now, this is in L1 log. Okay, of course, u is in L1 log. I erased u, but it is clear that u is in L1 log. see, it's clear that if you fix a compact, this is integrable in a compact set. So clearly U is in L1 log. Of course not in L1, but in L1 log, yes. Huh? So U is in L1 log. First fact. Next we can go on, because this now has a meaning. Everything is finite. So the first idea is, okay, I have a Lebesgue integral in dx dt. I can split it as, since this has 0 Lebesgue measure, it is not seen by the Lebesgue integral, so I can integrate over, it's clearly the integral of the same quantity. So just remove one line. And then, we agree? Yes. Trivial. Omega minus and omega plus are disjoint, so I use additivity. So this integral omega minus u pi p plus x plus integral omega plus u pi p plus p dx. Okay. Now, in omega minus, u is by definition constant equal to u minus. Because omega minus is this region and u you see is u minus. And in omega plus, u is u plus. Okay? So this is clearly equal to u minus integral omega minus phi t plus a phi x dx dt plus u plus integral omega plus phi t plus a phi x dx dt. It's okay? No mistakes for the moment? This is equal to this. Now, what is the boundary of omega minus and the boundary of omega plus? Okay, the boundary of omega minus is this one. And the boundary of omega plus is this one. Okay. Just portions of plane. Okay. And these are Lipschitz open sets. And okay, they are not bounded, but I can apply the theorem of Gauss-Green because phi has compact support. So at the end, I'm not integrating the whole omega, but I can cut with the big ball, and the integral is on omega minus intersected that big ball containing the support of phi. Okay, so I am in the position to, even if these two sets are not smooth, doesn't matter. Okay, so let me introduce another notation now. Let me introduce the jump, and then I introduce the normal to the jump pointing from u minus to u plus. So I indicate this as nu ju is the normal, unit normal, to ju from u minus to u plus. And this nu should be equal, so let me see, u minus, u plus, so it should be equal to, say, a minus 1 divided because the tangent, this is a characteristic, no? It's a characteristic. So the direction, you remember, is 1a. The tangent, the direction of this characteristic is identified by this 1a. So if I now exchange these two and change one sign, I get the orthogonal. No? So this vector is clearly orthogonal to this. Then I normalize, and then I take the negative component in this way, the second negative component. T is the first component. T is the first component. So this points down because its second component must be negative. I hope. Yes. Not sure. First component A is positive. Is this point? So if A is positive, this has its second component is positive. Negative first component. Or maybe there is a matter. Well, actually, this computation does not depend on the
I guess it should be this, because if we take that vector and bring in the origin, the second coordinate will be negative.
Actually, the second coordinate is positive, no? Because it is x. Okay, maybe this is from u plus to u minus. From u plus to u minus. Now, because t is the first component, so this vector, if a is positive, the line has this slope, right? So u minus is on the left, u plus is on the right, and the second component of this vector is the x component, which is positive actually. So maybe here I have to switch from u plus to u minus. So maybe I have to draw the other way. Right? So let's see what happens in any case. The computation will not depend on the choice of nu. So let me go on. So I am here now. Okay, and this is what is u minus integral over omega of the divergence of, in time space, a phi dx dt, where capital A is capital A was this. Okay. So this is a product of capital A, so 1 phi t plus a phi x, yes, plus u plus integral over omega plus the divergence of capital A phi dx. Correct? This is divergence in time space. Okay. And now I can apply the divergence theorem, as I said. So I can go on with computation. Maybe I can go on and u minus Then this is an integral of the divergence, so this becomes an integral of the boundary. The boundary now so it is the scalar product GU phi H1 plus U plus integral boundary omega plus scalar product A dot. Now there is instead I have to take here the normal to the outward normal, right? If I integrate an omega minus, the outward normal. So maybe this will be minus and plus. Maybe. But when I integrate omega plus, I have to take the outward normal of omega plus, which is minus the outward normal of omega minus. So this, independently of the choice of that minus or plus there, this is a minus. With the same mu. I convince you or not? Check, please check. I want everybody to be convinced or there is a mistake. So one of the two. Are you convinced or not? So I am applying the divergence theorem in this part. If I want to the volume integral become a surface a line integral, not the volume, the integral of the open set becoming an integral over this boundary with the plus in front, I need to take the unit normal pointing out to outward. Okay, so maybe this with the minus and with the plus. This is new. Then I'm integrating here and applying here the Gauss-Green theorem, so I need the outer normal, which now is the normal points outside, omega plus, before is minus the previous one. And so here there is a minus. I'm using the same vector here.
Then what about the real axis? I mean, in some way it belongs to the boundary?
The boundary of omega minus is this, and the boundary of omega plus is this, as I said.
Yeah, so I mean the vector that we are considering is just, I mean, the boundary that they have in common, or is the in bold?
The boundary of omega minus is this. The boundary of omega plus is this. So this integral is an integral over this, and this integral is an integral over this. This is your question.
Yeah, no, I mean, I was wondering because, I mean, for sure if you are integrating in this part, I mean, the normal of this part is in this direction, and the normal of this part is in this direction. But,
yes.
For example, in this part, the normals are, they coincide.
Yes, indeed. So, you're right, perfectly right. So, we are integrating on this part, and then indeed there is something missing. Because there is, it is not finished here. No? This concerns only these two, but then there is an integral here and an integral here. Okay, so omega minus, this is, let me call it Ju actually, and here it is still Ju. It's okay, and then there is the plus. Now the outward normal to this to omega minus here is first component is -1 and second component is this, no? Okay, so the first component, and here the same. So this is an integral u minus, so let me write it here, u minus integral over minus infinity 0, and here I have u plus integral minus infinity 0, Okay, and then I have this vector. This vector has only time component, negative time component. So it is minus 1, 0. Scalar product A phi. Capital A phi. Dx. Is it correct? Huh? Correct? So this is easy to compute because capital A was 1, so I erase it, but capital A was 1A. So this scalar product is just minus 1. So this is a minus and this is a minus.
The second integral
0 to infinity.
Sorry, 0 plus infinity. Okay, so this is just minus 1, this is just minus 1. Okay. Now I have to compute the scalar product between this and the normal. The normal is written here. In my notes, I think I am using this normal here, A minus 1. Okay, so the scalar product between this and this, okay, is simply 0. No, this is the important fact. So you see, even if you change, you use the other one, doesn't matter. The crucial fact here is that the scalar product between the normal to the jump and the direction of the characteristic line is. Okay. So this actually must be equal to minus u minus integral minus infinity 0 phi dx minus u plus, so maybe, okay, minus u plus integral 0 plus infinity phi dx, right? But then it's immediate to realize that it is nothing but the integral over r of u0 x phi of x phi of 0x dx. Because u0 is u minus in the negative, so I can put it inside, u plus in the positive, and it's immediate, no? But this was what? This was the starting point was to compute. So at the end, what we deduce? We deduce that we are deducing simply that we started from this computation, 0 to u phi t plus a tx, and we end up that this must be equal to minus integral u0 of x phi of 0x for any phi, and this is the definition of distributional solution. Because you remember, if you look at the notes, the distributional solution is this plus this equals 0 for any phi. So the crucial point in order this computation to hold is that nu ju times k is equal to 0 on j. So this is actually an L1 log distributional solution, so solution of our PDE. Now, natural question arises, what about the other solution that we wrote before? The solution that does not move the jump. Do you remember? So I leave you as an exercise now. Take instead the following function here. Then this is not a distributional solution. You can imagine why. Can you imagine why you redo this computation? Exactly the same. What is different? What is the difference now? The difference is that the jump set is not anymore along the characteristic. This is the characteristic line, but now you jumps here. No?
Then we disappear.
Then, I mean, this term will be the same. This will be the same. Because now we do the same. Now this is omega minus, this is omega plus. And these two contribute will be the same. What changes now is the integration of this part of the boundary, where we don't have anymore the condition, this is not 0 anymore. So, and that's because exactly for this reason that you can find a function phi for which the sum of the two is not 0. It's simple, it's enough to take a localized phi here. I mean, it's immediate to check that cannot be 0. So there is a term, one term more, which makes U not to be a distributional solution. So we have understood that now, of course, there is the problem of uniqueness, because this does not prove that that is the unique distributional solution. It just proves that we have found one distributional solution. We have found that another one is not a distributional solution, but we have not proven that the previous one is the unique distributional solution. So this is another story. So we postpone this question for a while on uniqueness of distributional solution. But I want to insist a little bit on this condition here. So let me give you an exercise. Let me give you an exercise. Question. So suppose that that u from as before, the same case as before, takes only two values. And suppose that the jump of u is a smooth C2, say, embedded curve. What I'm saying is that now if I look at Tx, I have u equal u minus here, u equal u plus, so jump. Okay, take a function u of this form. Is it true that so since the curve is smooth, there is a normal from u minus to u plus. Okay, that if u is a distributional solution, is it true that if u is a distributional solution to now the boundary condition, the initial condition in any case is not any more important, but u in a prolong. Resolution of satisfies because if it is true, it means that Ju must be the characteristic line. And therefore, at least among functions with two values, essentially we have uniqueness of distributional solution. At least among functions with two values. Is it clear, the text of the exercise? Is it clear? The test of it. I'm saying, suppose that you have a distribution. So, suppose that you have a distributional solution, we take only two values, u minus and u plus. So it jumps somewhere. Suppose that the jump is a smooth embedded curve. Okay? Like this. So u minus, u extrapolate u minus here, and u. But u is a distributional solution. So can I prove that knowing that u is a distributional solution, then this situation cannot appear, but necessarily the jump must be the normal to the jump must be orthogonal to A. So I leave you this as an exercise.
A is a constant? Or?
No, A is yes, it's a constant vector.
So the normal may change?
Huh?
Normal may change?
No. If this is true, it cannot change. It must be like this, constant.
Yes,
principle it may change, but if I am able to prove this, then posteriori it is obviously constant. Huh? No? Or maybe I have not understood your question. Maybe.
We are looking at the solution side spaces community, yeah?
No, I have a distributional solution. Is it true that then this holds? Which means, is it true that then this is constant and is always orthogonal to capital A? I don't know, is not clear? Which is the... For you is clear, the question for you? Why is not clear?
The question is clear, but the solution...
The solution,
question is clear.
This is an exercise. So it's no. Okay. Fine. Okay. Exercise. So I give you 3 exercises actually. So now let n go equal to 1, u0 in L1 log to sigma. Prove. So this exercise generalizes the previous example. In general, not only for a function u0 which takes 2 values only, but for any u0 in L1 log, prove that the function, the almost everywhere defined function is a distributional solution Is this statement clear now? We have proven this in the particular previous exercise was to prove this in the particular case n equal 1 and u0 taking only 2 values, u minus and u plus. What it is written here is that actually it is always true. So you cannot do the easy computations that we did before, splitting the integral into omega minus, omega plus, because there were 2 regions where u was equal to omega minus, u minus, u was equal to omega plus. U now is have infinitely many values. You cannot do that. Okay. Is this clear now? So 3 exercises for the next week. Home exercise. Okay. Now, once now we can pass to, if this is at least the statement of this exercises is clear, we can generalize our PDE. So we need now to consider a more complicated PDE, still transport equation, but we complicate the equation of the following form: ut plus a grad u equal c, and say u of 0z equal u0z for the moment on sigma. And let's come back. I don't want now to concentrate on the smoothness of the initial condition. I just want to keep to concentrate on the fact that the initial condition, let's suppose it is smooth, but now the problem is that we have C, which is not constant. So which are now the data of the new PDE, still a linear transport equation, which is non-homogeneous linear transport equation. Non-homogeneous linear transport equation, where u0, say, in C1 sigma, and C is a function of time space, which is supposed to belong, say, to something like this. Okay? What can we say about this sort of PDE? Okay, there is no time today, but at least one remark is clear. Do you remember the starting point of the first lecture? The starting point of the first lecture was that if here it is 0, then the derivative of u along capital A is 0, which means that u must be constant along characteristic lines, right? And it is clear that now this reasoning doesn't work anymore, because the derivative of u along capital A is the left-hand side. But this derivative now is not 0. So the situation is changing quite strongly. We cannot say anymore that u is constant along the characteristic lines. No? So, okay, time is over. This is what we will do the next time. But I leave you to start to think how one could adapt the method of characteristics. I will do this the next time, of course. But try by yourself, just for fun. Try to adapt. What could you do? What would you do? To this new situation. It's not immediate, so it's not so clear what to do. What I can suggestion, maybe I will do this, but just suggestion. You remember we wrote a system. The previous system of characteristics was the following. Do you remember? Y dot of 0 in the case equals 0. Do you remember? This was the system of. Actually, this was not necessary, but I wrote it at some moment. I wrote it because why don't we? Let's write it also in any case, even if it is 3. And then this produces, say, x of t semicolon z. This produces y of t semicolon z. And then we construct the map the diffeomorphism. The inverse was invertible, and the inverse was something that we call z of tx. Remember, this was the guideline. We have this equation system, we have this one equation here. This gives me this and this. Actually, this is not really relevant when a is equal to 0. Doesn't matter. I can define a diffeomorphism of Rn plus 1 into itself. This diffeomorphism is the identity in the first component. And also the inverse turns out to be the identity in the first component. And capital Z is the inverse of the remaining part. And then we observed that the solution was u0 of y okay. I think it was this, no? Please check in your notes at some moment. u0 of z, sorry, u0 of z dx. Yes, it was u0 of, because this is, yes, it was, I think it was correct. No, it was correct. Please check if this is consistent with what was written at some point. Well, because y is using. I think it was this one, no? Y of t of z of tx. Okay, because y is u0 because y dot is constant. Okay, so this is. Now, this is this was the main idea. System of characteristic, diffeomorphism, inversion of the diffeomorphism, computation of y along the inverse. And this magically is u of tx, solution of the initial PDE. Okay. Now, what happens if A is not only if A is C, sorry, here is C. Not B, C. So if C now is non-zero, the suggestion for you is that this remains the same. This remains the same. So the solution is before, but this changes. This changes and changes as follows. So this is T, so T and T. So this is T and T, everywhere. Okay, so this remains the same. This changes now. And so, but then, if you are able to solve, this is as before, in the previous case, same. This is different, but it's very easy because this is not an ODE. Because x of t is explicit from here. You put it here, and then you integrate. So y of t is just an integration. It's not a trivial ODE. It's finding a primitive. But once you have done this, you can still have the diffeomorphism, the inverse, and you try to see whether the same theorem holds. So this is not true anymore, but this may be still true. So the diffeomorphism is as before. This is as before. Y changes because y now is not constant anymore. Previous y was constant equal to u0 of z. Now y is not constant, but still maybe there is a hope that the same ideas work. So this is a suggestion.